There are several reasons why many utilities forbid the grounding electrode conductor connection inside of metering enclosures, even though it is often the best and most logical place to make the connection. Firstly, safety is a paramount concern. The metering enclosure is typically located close to the service entrance, where there is a high potential for electrical hazards. Making the grounding electrode conductor connection inside the enclosure could create a dangerous situation for utility workers and homeowners. Secondly, accessibility plays a key role. The grounding electrode conductor connection needs to be accessible for inspection and maintenance. Making the connection inside the metering enclosure would make it difficult for utility workers to access the connection if necessary. Thirdly, corrosion is a significant factor. The metering enclosure is often exposed to the elements which can cause the grounding electrode conductor connection to corrode over time. This could lead to a loss of grounding and create a safety hazard. Fourthly, tampering is a concern. The grounding electrode conductor connection is a critical part of the electrical system, and it is important to prevent it from being tampered with. Making the connection inside the metering enclosure would make it easier for someone to tamper with the connection, which could create a safety hazard. For these reasons, many utilities require the grounding electrode conductor connection to be made outside of the metering enclosure, in a location that is accessible and protected from the elements. Grounding is a critical aspect of electrical safety. The grounding electrode conductor, or grounding electrode conductor, serves as the primary path for fault current to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly trip and to energize the circuit. A properly installed grounding system helps to minimize the risk of electrical shock and fire. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes, that are bonded together and connected to the grounding electrode conductor. The grounding electrode conductor then runs to the service equipment, where it is connected to the neutral bus or terminal. The location of the grounding electrode conductor connection is governed by electrical codes and regulations such as the National Electrical Code, or NEC. These codes specify the acceptable methods for grounding electrical systems and equipment, including the size and type of grounding electrode conductor, the location of the grounding electrode, and the requirements for bonding different parts of the electrical system together. Metering enclosures, which house the electric meter, are typically installed at the service entrance where electricity enters a building or property. The service entrance is often a point of high electrical activity, with large currents flowing through the conductors. Making the grounding electrode conductor connection inside the metering enclosure might seem like a convenient and logical option, but it can present several challenges. Firstly, space constraints within the metering enclosure can make it difficult to properly install and maintain the grounding electrode conductor connection. The enclosure is often crowded with other equipment, such as the meter itself, service disconnects, and wiring. This can make it challenging to access the grounding electrode conductor connection for inspection or repair. Secondly, the environment inside the metering enclosure can be harsh. The enclosure is often exposed to the elements including rain, snow, and temperature extremes. This can lead to corrosion of the grounding electrode conductor connection, which can compromise its effectiveness. Thirdly, safety is a major concern. The metering enclosure is a potential hazard for electrical shock, especially if the grounding electrode conductor connection is not properly made or maintained. Utility workers and homeowners who come into contact with the enclosure could be at risk of injury or death. For these reasons, many utilities have policies that prohibit making the grounding electrode conductor connection inside the metering enclosure. Instead, they require the connection to be made outside the enclosure, in a location that is more accessible, protected from the elements, and less likely to be tampered with. Alternative locations for the grounding electrode conductor connection include the service entrance panel, a ground rod driven into the earth near the enclosure, or a metal water pipe that is bonded to the grounding system. The specific location will depend on the local electrical codes and the utility's requirements. It is important to consult with a qualified electrician or the local utility to determine the appropriate location for the grounding electrode conductor connection. When installing the grounding electrode conductor connection, it is essential to follow all applicable codes and regulations. This includes using the correct size and type of grounding electrode conductor, making a secure and reliable connection, and protecting the connection from corrosion. It is also important to properly bond all metal parts of the electrical system together to ensure that they are at the same electrical potential. This helps to minimize the risk of electrical shock and fire. Regular inspection and maintenance of the grounding system are essential to ensure that it continues to function properly. This includes checking the grounding electrode conductor connection for corrosion, damage, or looseness. It also includes testing the resistance of the grounding system to ensure that it is within acceptable limits. If any problems are found, they should be corrected immediately by a qualified electrician. In addition to the reasons mentioned above, there are other considerations that may influence a utility's decision to prohibit grounding electrode conductor connections inside metering enclosures. One such consideration is the potential for theft of service. If the grounding electrode conductor connection is easily accessible, it may be possible for someone to tamper with the meter and steal electricity. By requiring the grounding electrode conductor connection to be made outside the enclosure, the utility can make it more difficult for someone to tamper with the meter. Another consideration is the potential for damage to the meter or other equipment inside the enclosure. If the grounding electrode conductor connection is not properly made or maintained, it could create a path for stray currents to flow through the meter or other equipment. This could damage the equipment or cause it to malfunction. By requiring the grounding electrode conductor connection to be made outside the enclosure, the utility can reduce the risk of damage to its equipment. The NEC provides specific requirements for grounding electrode systems in Articles 250.50 through 250.70. These articles cover the types of grounding electrodes that are permitted, the methods for installing grounding electrodes, and the requirements for bonding different parts of the electrical system together. The NEC also specifies the minimum size of the grounding electrode conductor, which is based on the size of the service entrance conductors. The grounding electrode conductor must be large enough to safely carry fault current back to the source. In addition to the NEC, local electrical codes may also have specific requirements for grounding electrode systems. It is important to consult with the local electrical inspector to ensure that the grounding electrode system complies with all applicable codes. When installing a grounding electrode system, it is important to use approved materials and equipment. This includes using grounding electrodes that are listed and labeled for the intended purpose, using grounding electrode conductors that are sized appropriately for the application, and using connectors and fittings that are designed for grounding applications. It is also important to follow the manufacturer's instructions for installing the grounding electrode system. Proper installation is essential to ensure that the grounding system functions properly and provides adequate protection against electrical shock and fire. Regular inspection and maintenance of the grounding electrode system are essential to ensure that it continues to function properly. This includes checking the grounding electrodes for corrosion, damage, or looseness. It also includes testing the resistance of the grounding system to ensure that it is within acceptable limits. If any problems are found, they should be corrected immediately by a qualified electrician. In some cases, it may be necessary to install supplemental grounding electrodes to improve the effectiveness of the grounding system. Supplemental grounding electrodes can be used to reduce the resistance of the grounding system or to provide additional protection against electrical shock and fire. The decision to install supplemental grounding electrodes should be made in consultation with a qualified electrician. Grounding and bonding are critical aspects of electrical safety. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts of the electrical system are at the same electrical potential. Together, grounding and bonding help to minimize the risk of electrical shock and fire. It is important to understand the principles of grounding and bonding and to follow all applicable codes and regulations when installing and maintaining electrical systems. The utility's prohibition of grounding electrode conductor connections inside metering enclosures is a safety measure designed to protect utility workers, homeowners, and the public from electrical hazards. By understanding the reasons behind this prohibition and following the proper procedures for grounding electrical systems, we can help to ensure a safe and reliable electrical supply. There are several types of grounding electrodes that are permitted by the NEC. These include metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and ground rods, and pipe electrodes. Each type of grounding electrode has its own advantages and disadvantages, and the choice of which type to use will depend on the specific application and the site conditions. Metal underground water pipes are one of the most common types of grounding electrodes. To be used as a grounding electrode, the water pipe must be in direct contact with the earth for at least 10 feet. The water pipe must also be electrically continuous and free from any insulating coatings or joints. Metal frames of buildings or structures can also be used as grounding electrodes, provided that they are effectively grounded. This typically involves connecting the metal frame to a grounding electrode conductor that is connected to a grounding electrode. Concrete encased electrodes, also known as UFA grounds, are another type of grounding electrode that is permitted by the NEC. Concrete encased electrodes consist of at least 20 feet of bare copper conductor that is encased in concrete. The concrete must be in direct contact with the earth. Ground rings are a type of grounding electrode that consists of a bare copper conductor that is buried in a ring around a building or structure. The ground ring must be at least 20 feet long and must be buried at a depth of at least 2.5 feet. Ground rods and pipe electrodes are another common type of grounding electrode. Ground rods are typically made of copper or copper-clad steel and are driven into the earth. Pipe electrodes are typically made of galvanized steel and are also driven into the earth. The NEC specifies the minimum size and length of ground rods and pipe electrodes. The grounding electrode conductor is the conductor that connects the grounding electrode to the service equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor for different sizes of service entrance conductors. The grounding electrode conductor must be made of copper or aluminum and must be protected from physical damage. The grounding electrode conductor must be connected to the grounding electrode using a listed connector. The connection must be made in a manner that ensures a permanent and reliable electrical connection. Bonding is the process of connecting all metal parts of an electrical system together to ensure that they are at the same electrical potential. Bonding helps to minimize the risk of electrical shock and fire. The NEC requires that all metal parts of an electrical system that are likely to become energized be bonded together. This includes metal enclosures, metal raceways, metal piping, and metal equipment. Bonding is typically accomplished by using bonding jumpers. Bonding jumpers are conductors that are used to connect metal parts of an electrical system together. Bonding jumpers must be sized appropriately for the application and must be made of copper or aluminum. Bonding jumpers must be connected to the metal parts using listed connectors. The connections must be made in a manner that ensures a permanent and reliable electrical connection. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs work by monitoring the current flowing through a circuit. If the current flowing through the circuit differs from the current returning to the source by more than a few milliamperes, the GFCI will trip and energize the circuit. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or FCIs, are devices that are designed to protect against electrical fires. FCIs work by monitoring the current flowing through a circuit for the characteristics of an arc fault. If an arc fault is detected, the FCI will trip and energize the circuit. FCIs are required in many locations such as bedrooms and living rooms. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other events. SPD work by diverting the surge current to ground, protecting the equipment from damage. SPD are recommended for sensitive electronic equipment such as computers and televisions. Electrical safety is a critical concern for everyone. By understanding the principles of electrical safety and following all applicable codes and regulations, we can help to protect ourselves and others from electrical hazards. It is important to always use caution when working with electricity and to consult with a qualified electrician if you have any questions or concerns. Regularly inspect electrical cords and appliances for damage. Replace any damaged cords or appliances immediately. Never overload electrical circuits. Overloading circuits can cause them to overheat and start a fire. Use ground fault circuit interrupters, or GFCIs, in wet locations such as bathrooms and kitchens. GFCIs can protect you from electrical shock. Use arc fault circuit interrupters, or SIs, in bedrooms and living rooms. SIs can protect you from electrical fires. Install surge protective devices, or SPDs, to protect your electronic equipment from voltage surges. Be aware of the location of your electrical panel and know how to turn off the power in an emergency. If you smell burning plastic or see smoke coming from an electrical outlet or appliance, turn off the power immediately and call a qualified electrician. Never touch a downed power line. Downed power lines can be deadly. Stay away from downed power lines and call the utility company to report them. Teach children about electrical safety. Children should be taught not to play with electrical outlets or appliances. By following these simple tips, you can help to protect yourself and others from electrical hazards. Electrical safety is everyone's responsibility. Remember to always be cautious when working with electricity and to consult with a qualified electrician if you have any questions or concerns. Understanding the reasons behind utility regulations, like prohibiting grounding electrode conductor connections inside metering enclosures, is crucial for ensuring electrical safety and compliance. The grounding system is a fundamental component of any electrical installation, and its proper design, installation, and maintenance are essential for protecting people and property from electrical hazards. Therefore, adherence to these regulations and best practices is vital for maintaining a safe and reliable electrical system.